Given x of t is equal to a cosine omega t, what's the position at t is equal to 0 and t is equal to 2 pi over omega? Now, we learned in the last example that using a cosine is an equally valid way of describing simple harmonic motion. So this function we're looking at here is another description of simple harmonic motion. I'd like to draw a graph of this function because I think that will help me to think about what's being asked here a little bit here. So I'm going to try to draw some axes here. Since this is cosine of 0 is equal to 1, so it's starting at its maximum value. It's multiplied by a there in the function that's given. So I'm just going to start the graph over here and have it go down, and then it goes to some minimum value, and then it's going to come back up, and maybe I need a little more time axis over here. So let's label this is the time axis, this is the x-axis. So we've really graphed x versus t. The maximum amplitude of this function corresponds to this point right here. The minimum spot here corresponds to minus a, so that's how the parameter of a as an amplitude in this function relates to what the graph looks like. That describes that function. The first part of the question, when it says what's the position at t equals 0, well, that corresponds to t right here at the origin. And we've already said that that's equal to a, and that makes sense because cosine of 0 is 1. 1 times a is a. So my first answer should be a, and maybe I'll just write that as x of 0 is equal to a. The second one looks like it's going to require a little bit more work. And so for that one, I'm going to say x evaluated at 2 pi over omega is equal to a times cosine of, and let me use some parentheses in here, even though the parentheses weren't there in the original function. There, you can regard it as being implied, as we discussed on the key concepts slide, so I can bring them in for clarity anytime I want. And this will be omega multiplied by, for t, I'm going to substitute in the time I'm evaluating at, so 2 pi over omega, and these omegas look like they cancel, so I really just have a times cosine of 2 pi, and cosine of 2 pi is also equal to 1. It's when the cosine's gone through its full cycle, following kind of the unit circle, and at that point cosine returns to 1, having gone all the way to minus 1 and back, if you remember kind of how the unit circle definition of cosine works. So this is therefore also equal to a. Let's go ahead and check those answers there, and it says a and a. And then it notes that for cosine, there's no value for t between these two values with the same properties. Thus, the period is 2 pi over omega. In other words, this spot here on the graph where I completed a full cycle of oscillation for this harmonic motion, that is 2 pi over omega, the point that I evaluated at, but that's also equal to what was defined to be the full period of a harmonic function.